So we have this in um, another spot. It's not in a regular spot. This is under the Miami 4450 course, and it's called a bit of digital logic. Everybody follow that? So we go under the Miami 4450, and it's a bit of digital logic. It's chapters 2, 3, and 4 of the Floyd text, and we really don't. We kind of stole 3 chapters. I don't know exactly how I did this, but somehow I managed to get it without too much difficulty, whatever. So we want to talk about a couple, 3 things that are important to us. And basically, we want to understand how a programmable controller understands numbers, and also how we can flip back and forth between a binary and a decimal number, and that sort of thing. That's chapter 2. Chapter 3 is about gates and logic, and chapter 4 is more about some laws and that type of thing. And we get into the De Morgan stuff in chapter 4, and we'll talk about that. And they're kind of interesting rules. Anyway, we want to talk about numbers, and obviously there's decimal numbers, and if it's the number 23, it's 2 times 10 plus 3 times 1. And if it's a binary number, it is based on base 2, and you have bits, and they correspond to a number. Okay, so that would be a 4-bit number, would be from 0 through 15, and the power of this would be 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. So if you were to try to look at a number and try to figure it out based on whether it's a 1 or a 0, you would add that particular number to your number. Okay, so now we're going to talk about binary to decimal conversion. And how you do this is you can add up. If there is a 1 in its place, you add that power. All right? And that gives you a decimal number. And you can also do it with decimal numbers, binary decimal, but we very rarely, if ever, use decimal numbers with binary. You can forget about the decimal numbers in binary. It's never done. Now, decimal to binary conversion. This is something that you could be asked to do on a test, and there's 2 ways of doing it. One way is to look at the powers and subtract them off. In other words, if you have a number and then you subtract off, let's say for the number 8, you'd say, well, excuse me, number 12, it is 8 plus 4 plus 0, so it's 2 to the 3rd plus 2 to the 2nd, and there are your bits. All right? So if you know the powers of 2, you can subtract off and then see the remainder and just keep going, and that would be how that's done. There is another called a repeating division by 2 method that is pretty neat, and it will do the job for you very well. And what you have to do in this particular method is to take the number, divide by the base that you're converting to. So this would be a decimal number, divide by the base, and your answer would be 6, and put the remainder out here. Then you take 6 and divide by the base, and it would be 3, and put the remainder out here. You divide 3 by 2 is 1, put the remainder out here. Divide 1 by 2 is 0, and put the remainder out here, and then you do bottom up, bottom to top, 1100, and that's your number, 1100, and it always works. Bottom up, bottom to the top, that's your number. Okay? You go until this number is less than this number, and then you get your remainder, and there's your number. Here's the number 19. 19 divided by 2 is 9 with a 1 remainder. 9 divided by 2 is 4 with a 1 remainder. 4 divided by 2 is 2 with a 0 remainder. 2 divided by 2 is 1 with a 0 remainder. 1 divided by 2 is your final number. And many people don't even do this divide by 2. They bring this number down. Excuse me. If the number 1 is less than number 2, you're done. And you read it this one, then this one, and this one, and this one, and this one. And that's typically how it's done. Or you can do it like this. So if this number is less than this number, you stop, but you then have to remember that you read 1, 2, 3, 4, 5 bits in this order. 1, 2, 3, 4, 5 in that order. 1, 0, 0, 1, 1. Typically that's what's done, except for the fact that these guys decided to say, no, we do a remainder, and then whatever. You stop after that. Okay, any questions about division by the base? Because this could be, how do you convert from base 3 to base 10? Divide by 3 and do bottom up. How do you convert from base 4 to base 10? Same thing. Okay, this is a universal approach to finding the conversion from base to base. Okay, now the good news is most of your calculators can do this on their own. You can actually do this on your calculator, and you have free access to your calculator. You can do that way. But again, I want you to understand that this is a possible answer or possible question that you might have to answer. And also, I'm going to be giving you weekly quizzes. They're to be looked at over the weekend and handed in on Tuesday. They're Monday. They're really not a quiz. They're just kind of like a homework / let's see how to do this type thing, and that'll be handed in the following Monday. So I'm going to be giving you those starting tomorrow. So hopefully you'll get an email tomorrow, and you'll have a little attachment to it, and you'll look at that and say, now what is he asking for? And then you'll figure it out. It might be this, it might be something else. I don't know what it'll be for the first couple, but anyway, it's just good practice. And I'm asking you to be able to do this kind of stuff because this is stuff that is easy to ask on a test. They're easy questions. They're not hard questions, but they are, anyway, they're what they are. Again, I am not going to ask you for the decimal point because typically in a PLC or in a computer, they do not imply a decimal point in a binary number. So again, this is after the decimal point to the right, but I also am going to say it again. Binary numbers, usually you don't represent fractions, all right? If you have a number, what's the ideal way to handle any number in a computer? A real, okay? A real number. In other words, not an integer, but a real. Now, what's the downside of reals? They're accurate to 7 places. Well, that should be good enough, right? 7 places is good enough. If you have an extremely large count, sometimes it's not. And if you want to use a counter or a time-based, that type of thing, usually when you're counting in whole numbers, integers are okay. And also, what I mentioned the other day was that sometimes an integer is an integer now and it's control bits later, and they go back and forth and back and forth and back and forth. That is extremely hard to do with reals, but you can do it with binary, with integer numbers. Okay, so you can treat an integer number as 16 or 32 bits, or you can treat it as a number, and you can continually go back and forth with that, and people do. So you need to know how to do this part of it. In other words, the power of 2, and how to, basically just know that there is such a thing as an integer number, how it's stored, okay, how it's stored in a computer, how it's stored in a PLC. It's the same thing, okay? A PLC is a computer, so basically how that number is stored is very important. Now, we get down to arithmetic, binary arithmetic. Well, guess what? You can add, subtract, multiply, and divide integer numbers. Anybody not believe that? Anybody not believe that you can add, subtract real numbers? You can add, subtract, multiply, and divide integers and reals in a program controller or in a computer. So there's nothing new that you can, just basically, how do you do it? Well, you can add, you can subtract. Okay, subtraction is a bit of a sticky issue. Okay, so you got to do this borrowing aspect of it. So there is another way of subtracting, and it is called, there's binary multiplication and binary division, and we will not do either of those. We will do a subtraction using a complementary complement a number. Okay. Now, this is not, oh, you're looking good today kind of compliment. This is a C-O-M-P-L-E-M-E-N-T. Complement means the opposite of something. So what would be the opposite of a positive number? It's a negative number, right? So how do you find the complement of a binary or a binary integer or of an integer? How do you find the C-O-M-P-L-E-M-E-N-T of it? Okay. Well, in order to find the negative of a number, you flip the bits and add 1. In other words, you take all the bits and then you flip them and then you add 1. That's called finding the 2's complement. So what is the 2's complement of this number? It is this number. All right? So you flip all the bits and then you add 1. Now there is an alternate approach, and I like the alternate approach because it is, as they say, it's kind of tricky, but it works, and it's very good. Okay, so the other approach to doing this is, and I'm going to go down through here in just a minute. Okay, so I'm going to show you how to find the negative of that number right there. Okay. Now, what would be the negative of that number? Well, I don't know, but can everybody see that, or is that too small? I can make that a little bigger. I think I can make it a little bit bigger. What is the negative of that number right there? And that's the typical kind of question you're going to get. All right. What's the negative of that number? Well, it's this number right here, okay? Now, no, this is, I'm sorry, right? The 8-bit number, and okay, and okay. Now this is not it, okay? So, 8-bit number and assignment, okay, that is not it, okay? Forget about that. This is right here is nope. This is what we want. We want the 2's complement of a number. All right. So all right, so how do we do that? This is a number here. It's 010101110, okay? And it is a plus 86. Now this is an 8-bit number. Get used to 16-bit numbers as well. So we don't do everything in 8-bit. Sometimes we do it in 16-bit. But this would be a 8-bit number. Now in 8 bits, how would you represent a minus 86? Well, the leftmost bit is a negative. Everybody notices that it is a negative. In other words, this would be 1, 2, 4, 8, 16, 32, 64, 128. But if the leftmost bit in signed arithmetic is a 1, it means it's a negative 128. Okay? It's not a positive 128, it's a negative 128. Now you can have unsigned binary or unsigned integers, and you can have signed integers, and you have to be careful which one you designate, because sometimes you can designate the wrong one and then you get an erroneous response. But if you say signed integers as your type of number, this is what you get. The leftmost bit is a negative of that. So this would be a representation of a negative 86. Notice, it is not the same bits. This is the negative of this. This is the positive 86, this is the negative 86, and these bits are not the same as these bits. Everybody agree with that? So how do you find the negative of a signed number? How do you find the negative of any signed number? Well, you can do, like we said at first, you can take a number, and this is, again, I'm going to have to go through this part of it. Okay, so this is the part here that we really do want to concentrate on, okay? So, if I have a positive number and I want to take the negative of it, I do the following. I basically do what they did, or I can do this. So that, okay, I can say, here's the number right here, 0.0000111, and I can say, let's just take a general number. I'll take an 8-bit number, 01001000. Now that's an 8-bit number, and I want to find the negative of that. Okay, that's a positive number. And what is it? It's 1, 2, 4, 8. So there's an 8, 16, 32, 64. So the number is 64 plus 8, or 72, right? Now, how would I find a minus 72? Well, one way would be to take the bits, flip them all, 1, 0, 1, 1, 0, 1, 1, 1, and then add 1. That's one way of doing it. And then you add 1, 1 is a 0, 1 and 1 is a 0, 1, 1 is a 0, 1, 1, 1, 0, 1. Now, is that one? Okay, so that's 1011, 1000. Now that would be a minus 72. How do you know that that's a minus 72? Well, if you add this number to this number, you should get 0. And let's do that. 0, 1, 0, 0, 1, 0, 0, 0. Add to that 1, 0, 1, 1, 1, 0, 0, 0. Okay, add these two together and see if you get 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, carry of a 1. So that is a negative 72. How would you check it another way? You would say, well, this is a minus 1, 2, 4, 8, 16, 32, 64, 128, excuse me. 1, 2, 4, 8, 16, 32, 64, 128. So that would be a minus 128 plus 1, 2, 4, 8 plus 8, 16, 8, 16, 32. And if you add these all together, I bet you get minus 72. 32, 48, 48, 56, minus 128 plus 56 is equal to 2 and 7, and that's it, 72. That's a minus 72, so it's a minus 72. Minus 128 plus 56, or 56 minus 128 is a minus 72. All right? So, now this approach is very good, but there's another approach. Okay, so this approach right here is this is not the preferred approach. The other approach that is used more commonly to find the negative of a number is the following. So I'm going to do the following: 0, 1, 0, 0, 1, 0, 0, 0. Okay? Now I want to find it using an alternate approach. This alternate approach is to carry down the number as long as you have zeros. And then the first one you hit, carry it down, but then flip the rest of them. From that point on, you flip the bits. And notice what you have. You have the same thing here as you have right there. So after you carry the first one down, you flip the rest of them. And I draw this little arrow to remind you that from that point on, you flip the bits. That works. And it's a very effective way of finding the 2's complement of a number. So if I ask you to take a 8-bit or 16-bit number and subtract another number from it, if you were to take the first number, then take the second number, take the 2's complement of it, in other words, the negative of it, and then add the first number to the 2's complement of the second number, you're doing the same thing as subtracting. And that's the way computers do it, and that's the easiest way for you to do it. So anyway, let's do that. Okay, so let's just look at a typical situation where I would say subtract the second number from the first number. Okay, so it would say 0, 1, 0, 1, 1, 1, 0, 0. Okay, so that's my first number. My second number is 0, 0, 1, 0, 1, 1, 0, 0. Okay, so now I'm going to subtract this number from this number. Now, how do I do that? Okay, I can physically go through and borrow and do all that stuff, or I can do the following. I can say, okay, I find the 2's complement of this number, and then I add it to this number. So let's do that. Find the 2's complement of the second number. So I bring it down 0, 0, 1, but then from that point on I flip 0, 1, 0, 1, 1. Does everybody see that? This is 0, 0, 1, and then I flip 0, 1, 0, 0. So this is the negative of that number right there. And then I add this number to it. A lot easier. 0, 0, 1 and 1 is 0, carry 0, 1 and carry 1, 0, carry 0, and I'm gone. So now let's just see what that is. So what is this number here? I don't know, but I'm going to do it. I'm going to flip it over to decimal and see if I can get the answer. Okay, so this is 1, 2, 4. I've got a 4. I've got an 8. I've got a 16. No, 32, and I've got a 64. What is that number? Well, it is 64, 70, 80, 90, 92. So this is the number 92. What is this number right here? It's 1, 2, 4, 8. So I've got a 4, I've got an 8, 16, 32, and I've got now what? I've got a 44. So what is 92 minus 44? There's an 8, there's a 4, so I got 48. Now is this 48? 1, 2, 4, 8, 16, and 32. Daggone it, 16 plus 32 is equal to 48, and I proved that I can do that. Now, why are we doing this? Are you ever going to do this in a PLC? No. Why are we doing this? So you can recognize negative numbers and positive numbers in a PLC. If it's a signed integer, how do you know it's positive? If I have a 16-bit number, okay, I have a 16-bit number, and I'm using it as a number, how do I know it's positive? Look at the leftmost bit. If it's a 1, it's a negative. If it's a 0, it's a positive. Any questions about that? What about a 32-bit integer? Same thing. Okay? And if I declare a number as a signed integer, I am saying use that leftmost bit as the signed bit. If I declare it as an unsigned integer, I'm saying use it as a positive number. So I have a choice. All right? And that's how numbers are stored in a computer, in a PLC, and that's how they're done. So if you can add and subtract integers, this is how it's done. And that really is all you need to know about that. Now, there are things that can happen, like overflows and all that kind of stuff, and you can get errors. Now, what if you add two negative numbers and get a positive number? Or let's just say there are things that can cause errors. And we usually don't talk about it very much, but there are ways that you can have overflows and all that kind of stuff. You got to be very careful with integers. There's a lot of times you want integers, but you got to be careful with them because they have limits. They don't have fractions. They don't have other characteristics that you might want, but you do use them. You use them a lot, integers, 16 and 32-bit integers. And you can use 8-bit integers in Siemens. You can't in Allen Bradley. Allen Bradley is a little bit different, and I can give you all examples, but you can have an 8-bit, a 16-bit, or a 32-bit integer in Siemens land. You can have a 16-bit or 32-bit in Allen Bradley, and you can't get the other one. And I'm going to throw you another curveball. There are variant variables now as well. What is a variant variable? We don't use them hardly at all. We don't use them at all in this course. What would be a variant variable? Well, now I'm an integer, now I'm a floating point, and I can go back and forth and back and forth and back and forth and back and forth. What's the cost of that? It takes a little bit longer to execute the instruction. But you can actually have variant variables in the PLC now, as well as declare it as an integer, declare it as a floating point or as a real. You declare them, but yet, and you have to sometimes be very careful how you store the number because it can give you an error if you get the wrong type, and you'll see this as you go along. So we do have to talk about basically how numbers are stored in general. And here's an overflow. That's not good. So you have two positive numbers and you get a negative number. How can that be? You can't. How many of you have ever added two positive numbers and got a negative number? But if you are in 16-bit signed integer numbers and you do an add, this can actually happen, and that's not good. But it can happen, and you've got to be careful. Okay, and again, I'm going through this very, very, very quickly. Hopefully you'll read a little bit about it, and I'll give you a question or two, and I'll give you some questions, the old questions on a test that you can look at, and you can say, what is he going to ask on a test? Not much. But I definitely, there's 3 or 4 things going on in my head, but this is one of the major ones here, is being able to understand what a binary number is and how it's stored in a computer, a PLC in a computer, basically the same. Okay. All right, so yes, you can have multiplication and division, but we never worry about that because it's done automatically. Okay, so we get going here a little bit more, and there's some problems at the end of this chapter, and we're not going to worry about that right now. Now, a hexadecimal number is a combination of 4 bits per number of the hex. And when I first started programming, I got to the point where I thought in hex as opposed to decimal, because everything was based on hexadecimal numbering, and I was actually better at handling hexadecimal than I was actually decimal numbers for quite a while. But here is the example of hexadecimal. They take 4 bits and they cram them into a number, and after you get past 9, you go A, B, C, D, E, F. That's all it is. So if you see a number that's got A's and B's and C's and D's in it, you automatically think of it as hexadecimal. And you can convert. Binary to hex is very easy. Conversion from hexadecimal to binary is very easy, very, very straightforward. Conversion from hex to decimal is not so easy. How would you do that? Divide by 16. You follow me? Instead of divide by 2, divide your decimal number by 16, and out pops the hex numbers. And that's it. That's how you do it. So you can store bigger numbers more crammed together in hex than you can in decimal. Any question about that? There's your decimal to hex conversion. There's your answer right there. Divide by 2, divide by 16, divide by 16, divide by 16. I'll plop your answer. Can you add and subtract in hexadecimal? Yes, of course. It's just binary. It's just crammed in binary. How about other brothers, other types of operating systems or whatever? What is octal? Base 8. Octal. OCT, 8. Are there any computers that have octal in them today? The answer is probably no. There may be a few. Now, where did octal come from? Octal was the base numbering system for a PDP-8. Okay? And in the late 1960s, early 1970s, the PDP-8 ruled because they were the small computer that actually could run Fortran and other systems that could actually do programming on a factory floor. PDP-8s were base 8. And then along came PDP-11. How many have ever heard of Digital Equipment Corporation, DEC, D-E-C? Anybody? A few? Very few. If you want an example of a company that thrived and then went belly up, it's Digital Equipment Corporation, American corporation, and they're in Massachusetts, suburb of Boston. I actually went to PDP-11 school, so you're looking at a live person who actually went to PDP-11 school, and it was tough. They made us sweat. And anyway, it was base 16 or hexadecimal. It was 16-bit words, not 12-bit words, 16-bit words. And PDP-8 was the first computer on the factory floor to crack the $30,000 barrier. So they were the first people under $30,000 in that era. Now you say, you're kidding me. No, in the late 60s, you would buy a computer and it would be $75,000 or $100,000. People just didn't do it. And PDP-8 was the first one that cracked the $30,000 price barrier, came down below $30,000. Digital Equipment Corporation. If you're interested in history, read that history of that company and how they made bad decisions back in the 80s and 90s, and they went out of business. Yes, companies do go out of business, and they were ones that did. So anyway, that's octal. That's the history of octal. Octal to binary conversion, binary to octal conversion. On and on and on we go. Now, BCD is strange because what they do is they store 4 bits and they're a number from 0 through 9. Now, why would we ever have that? Why would we ever have BCD? Why is BCD still out there? Because we have things like scales and things that still have not a computer display, but they have single-digit displays. In other words, you would have numbers, and there would be 4 lines to each of those individual numbers, and those lines would represent 0 through 9. So in order to output from the computer to the number, you would have 4-bit lines, and those would represent a 4-digit number, 0 through 9,999. Okay, so you'd output 4 bits that would represent a number from 0 through 9. So BCD is not binary. BCD can convert to binary, but what you have to do is you have to convert from binary to decimal and then to binary. From BCD, you convert from BCD to decimal and then to binary. All right? That's how you do it. BCD and binary are not the same, and it's very rarely used. Why is it very rarely used? Because we got away from single-digit displays. You don't see them hardly at all anymore. You might see them on an old gas pump, like a Nixie tube or something like that, but you don't see them hardly, maybe on an old scale at a grocery store. But very rarely do you see them. Now all you see is a little display, right? A lot cheaper to put a little display there than it is to put individual decimal numbers that are individually given. Much cheaper to put a display up. Well, we don't see BCD anymore, but there's what it is. That's BCD, okay? Again, not to worry about BCD. Digital codes. Why would we have codes? It's flu season, right? Everybody's got a code today. No, that's a different kind. This is gray code. Now, why would we have gray code? All right. Gray code is a coding system that is used to, if we have an encoder, an absolute encoder. An absolute encoder is a rotary device that you can read bits off of, 4 bits, 8 bits, 12 bits, whatever. And if you are reading on a crack, okay, if you're reading on a crack, you do not want to be more than one number off. So you only change 1 bit at a time with gray code. Gray code is almost the same as counting in binary, but it's not, because you change one, when you're moving from 1 bit to the next, you're only changing 1 bit. So if you're reading an error, you're only off by 1 number. So if you're reading on a crack, if you're reading between two, if you're right at the point of, like in here, if you're reading this, and this one might be a 1, this might be a 0, and this might be a 1. That's not gray code. Here, if you have, at any one point in time, see, at any one point, there's only 1 changing. You follow me? That's gray code. Again, there is a conversion between gray code and binary. I'm not going to ask you to do that, but that's what that is. So if you have an encoder, an absolute encoder, and most of the time we don't anymore. We have incremental encoders. We do not use absolute encoders. Why? These things are made out of glass, and they're in a motor. Anytime anybody takes a hammer to that motor to do something to it, what happens to the glass encoder? Any ideas? Yeah. Not good. So a glass encoder in a motor is not advised. Incremental encoders are advised. What's wrong with the incremental encoder? You got to go 1 time around to find your home position, because there's a bit that says I'm home, and then it's just one or the other. It's just on and off, on and off, on and off the rest of the way around. But if you put a battery in an encoder, an incremental encoder, now you save where you were at any point in time, and that's why almost all motors, servo motors that have an incremental encoder on them, have a battery in them. So now all you got to do is every 5 years remember to replace the battery. So you don't have to do this. But anyway, that's about it. Now, let's keep on moving here a little bit. We got a little bit more time. Error codes. Parity. What is parity? Well, if I have even parity, that means that if I have an even number of 1s in my word, I put a 0 out to the side, because you add up all the 1s across plus a 0, you have even parity. Now, why would we even worry about parity? If a bit goes bad in your computer, parity will detect it and give you it'll flag that word as wrong. It'll flag it. And you say, is that practical? Yes, it's very practical. That's why we have parity in a computer system. If you have a system that does not use parity control or parity checking, you're risking not getting a correct number. But there are other ways of doing the same thing. One is called CRC, one is called LRC, cyclical redundancy check and longitudinal redundancy check. And the CRC is the best one, and the other one is LRC. But I'm not going to get into those. Those are error checking methods for transferring of information between 2 devices. So you might say, if you ever want to go back and look at this, you can. But CRC, how that's done is right here. and LRC is the other one. There are ways to guarantee that you're getting the number through correctly. And there's Hamming code. I don't know anything about Hamming code. You say, is error checking in information extremely important? Can it be important? Well, yes, it can be. And I'll give you an example. I worked in a number of side jobs when I was teaching. For a number of years, I needed to make the money, and I did consulting. So the summer of 2001, I worked in a rendering plant. What is a rendering plant, right? A rendering plant is where they cut up beef or pork or whatever. But in this case, they were processing the most beautiful cattle in the world, and about 100 an hour. So they were bringing them in, they were chopping them up, and they were sending them out as hamburgers, steaks, and everything else. And my job was to capture the information, the weights and the numbers and all that kind of stuff, and put it to the higher level computer. And I did that. That was what I did for the summer. It's my job. Anyway, that's what I did. Now, one of the things that I did do, and I was very scared about this, is what's after my name? If you looked at my thing, what did it say? William Ted Evans, PhD, PE. Okay, so what does that mean? What does PE mean? Can be sued. That's what that means. And now, and you take that with the programming. It means professional engineer, but I'm being funny. It's trying to be funny. Maybe I'm not. I don't know. Maybe I just scared half of you that just took your fundamentals test. I probably scared you into thinking, I don't think I want to take that test again. Anyway, so the number that came in for the rancher's weight, the cow's weight, had no parity checking. It had nothing. Okay? Now, how much do you think that made me feel as far as that number that came in? It was a number that, there was errors that possibly could pop into those numbers as well. How do you think that made me feel? There was no error checking at all in that number that came in. Very sketchy, because if somebody would go back and look at that code and say, now there's nothing coming in here that says there's a parity check or a CRC or any kind of error checking in this number, that's money, because the rancher was paid on the number of pounds that beef was weighed at the time that it was slaughtered. That was their money. 6 months after that, that company went belly up. And do you know what I did? Breathed a sigh of relief, because I knew that if they ever looked at that and said, now, who was ever doing any error checking? If a bit failed or something ever failed, what would happen? They would go back and say, now, you decided how to do that. I programmed something that somebody else bought, but that's not a very good excuse. But anyway, I took the money and ran, and that was it. But I tell you that you don't think you can walk into things seriously? And what on earth? But I did. I said, after I looked at it, I said, you got to be kidding me. There's no error checking of any kind in that number. No way of proving that number is what that number said it is. And plus that, there's noise coming in on that number. And I know how I did it. I know how I got the number. There would be noise coming in, and then I would look at the number. There were ASCII characters. And then there's a decimal point, and then there's some more ASCII characters. And how did I find the number? I looked for the decimal point, and I went to the left until I saw noise. And then I said, everything to the left, everything to the right of that is the valid number. But when I saw noise, there were FFs. FF, Frank, there would be noise. That would be all ones. So everything to the right of that, I took as a number. And then I did a reasonableness check. So how much does a cow weigh? 1,000 to 1,500 pounds, 1,200 pounds, 1,300 pounds. So I said, if it's reasonable, take it. And I did. And that's how I wrote it. But there was no way I knew exactly if that's right. And if a bit slipped or something, I had no way of knowing. He's saying, how can you possibly ever survive in an environment like that? I'm still standing, but that was the kind of thing that you say, how do you ever walk into things like that? It can happen, okay? So is parity checking or error checking important? Should you specify that when you're buying equipment? Should you specify that when you're putting equipment in? Yeah. Okay. I doubt if they still have that in that system. I don't know, but I doubt if they still do. That was in 2001. That's chapter 2. Now we're going to get through a little bit of chapter 3, but not much. So review this. It's in that chapter. It's in the MIME 4550 course. It's called a bit of Boolean, or a bit of Boolean, and just make sure you can do the 2's complement and then subtract 2 numbers. And if you can do that, you're in pretty good shape in that chapter. Okay. Now, the next one is the pictorial one, and this is the one that I want you to understand that these symbols have meaning, and they are the same symbols. This symbol right here is the same symbol that you're going to see in the programmable controller in the FBD language. So in the programmable controllers that you're going to be using, they're not like this one, but they are exactly like this one. So you can write your logic and connect things in the PLC just like you do here. It's exactly the same thing. Okay? So these are gates. You see, I've never seen anything like this before. Well, now you have. Okay? There is an AND gate. How do you remember an AND gate? That looks like a what? A D. A-N-D. And. A-N-D. Okay? So and a D go together. What is that symbol right there? An AND. There's your tip-off that it's an AND gate. Okay? So it's this and this give you this. That's Boolean logic. Okay? Oh, I can have 3, I can have 4, I can have 10 coming in on the left-hand side. But they all have to be the same in order for this to work. They'll have to be 1s. Okay? There's your truth table for an AND. Okay, now what can I ask with this question? I can ask you a question about timing diagrams. This is a timing diagram. Time is the x-axis. The value is the y-axis, 0 or 1, 0 or 1, 0 or 1, 0 or 1, okay? So I can ask you a question like this with something like this. That's legal, right? I can ask you that. So basically it is an analysis by each time and see what the answer is. And I can ask that with a combination as well as just one. In other words, I can have a combination of ands and ors and nots. Okay? So again, as you're reviewing this chapter, make sure you look at these timing diagrams and you at least have an idea what he's asking about. Okay, so here is a timing diagram for an AND gate. And that would be on the oscilloscope, or a data logic analyzer, which is a kind of an oscilloscope. And this would be an example of a logic problem using AND gates, okay? The OR gate. So now we're moving from relays, we're moving to discrete devices. But we talked about relays the other day, didn't we? And we're now talking about discrete devices, which then you can use to build logic from. What is it about an OR gate? Well, it's not a D, so it's got to be an OR, right? What is this symbol? Greater than or equal to 1. Well, if this is on and this is on, this would be a 1 and this would be a 1. Greater than or equal to 1, it means you add them together, and if any of them turn on, it turns itself on. Does everybody see that? If they're all a 0, it does not meet this condition. But if one of them are on, it meets the condition, greater than or equal to 1. So this symbol right here is the tip-off that it's an OR gate. That is saying at least one of them has to be on for it to be a 1. And there's your timing diagram. And another timing diagram. And they use the plus sign for OR. So if you write it as Boolean, if you write it in Boolean, you say A or B. If you write and, you would write A dot B. Okay. We're moving quickly through this stuff because I just don't want to spend a lot of time on it, but on the other hand, I do want you to understand that it's important. Now this is a negative, or a NAND, not AND, okay? Not of an AND. So here would be A or B. So what would this be? This would be the not of A and B, right? So it is on when you're not ANDed, and it is off when you are. When you have both of them on, it's off. So it's the not of an AND. There's a little bubble. The one for the symbology for the PLC is a little, I think it's the same. I'm not sure, but it looks like about the same. And a NAND is the same as a not of an OR. So if you take the two signals, not them, and then you OR it, so a NAND is the same as a not OR. It's the same thing. And a NOR is the same as a not AND. Okay. Again, moving quickly. A NAND. A NOR is a not of an OR, which is the same as a what? The not of an OR. This is an OR, not a NOR. And the NOR is what? It's on when they're both off. That's the only time it's on. Okay. So you can build gates. Not Bill Gates, but you can build gates. The exclusive OR is a symbol that's a little different, which is this. When it's equal to 1, this is on and this is off, it turns on. This is on and this is off, it turns on. So one of these is equal to a 1, but not both. Okay? And the symbol with the old style is that right there. Exclusive OR. But the equal one is the sign, that's the one that we will use. That's the one that's used in the programming language. Okay. And we talk a little bit about programmable arrays and moving from discrete devices to more sophisticated devices. You can have these. We don't really care about them other than the fact that you can spend your whole life programming these if you want to. Okay, nothing is that important. We gotta keep going through this. So at the end of this chapter, there are a few of these timing diagrams, and you might be interested in just practicing and looking at them a little bit. More here than we need. But it's something you can go back and look at from time to time as you need this in the real world. If you want to go back and look at it, this is the gut or the heart of the digital logic course that people take, chapter 2, 3, and 4. The rest of it, they're important things. I'm not taking the whole course in one night, but I'm taking the most important parts of it and kind of giving you a heads up about how that works, because that's what you need to know in order to be able to use those numbers in a computer, and also the gates, how they're physically arrayed, that type of thing, what they are, and how to go back and look at them and see what they look like. Okay, and a timing diagram. Timing diagrams do come into play from time to time. Not often, but they can be used. Okay. Moving along, chapter 4. We're not going to get through this. This is going to take more time than what we have just tonight, but I want to get you into chapter 4, where we're going to be talking about and they talk about in chapter 4 a lot more than I really care to talk about. But in chapter 4, they talk about how to simplify and to come down to the smallest possible how to simplify your logic. And I'm going to tell you in general that that's not profitable. If you look at most programs, they're not simplified down to the easiest or the most subtle, The reason why is because if it works, especially in a factory, don't touch it. And if somebody says, go back and make that simpler, that never is asked. What is asked is, does it work? And if it does work, don't touch it. If it doesn't work, fix it. So basically, you're not being asked to prove something with binary laws. You're never asked to write the most simplest equation, but you are asked to make sure that it works, okay? So these are some of the rules for Boolean algebra, okay? Now, I'm not going to belabor these, but they're there, okay? And I'm going to just tell you that you can get excited about them or you can not get excited about them. But A or 0 equals A or 1 equals A1, A and A0 equals 0, A and A1 equals A or A equals A or A naught equals 1. It's either on or it's off. You're always on. It's always 1, okay? A and A naught is always a 0. The knot of A is A. That is kind of important, okay? The knot of the knots is back to the original. A or AB is A or A naught B is A or B. A or B times A or C is A plus BC. Again, you don't have to remember these. You don't have to remember any of this stuff other than just the fact that they exist. And there's examples of these laws. Okay, now, from this point on, there is one more thing that we really do want to camp on, and it's called De Morgan. Simple reason, how do most of you think logically? Well, never thought of that. How do you think? Do you think in positive logic or do you think in negative logic? How many of you think positive logic? Most of you do. I guarantee you do. Okay? How many of you think of negative logic? Not very many. And I'll give you a clue. If you can't find something that you want to do, and you think, now, what am I trying to do here? It's the negative of something, okay? But it's more than one thing. It's more than one signal. It's 3 or 4 signals are being put together. You say, now let's think about it from the positive side, and then take the De Morgan, or the flip of it. You've got the negative, and it works, okay? And you say, what? That actually works? And it's one of the few areas from digital logic that you can actually use in your programming, in any kind of programming, but especially in PLC programming, in logic on a factory floor. It's one of the few tricks that you can actually take with you from digital logic and use. It works. And it works very, 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 very well. and I'm not going to try to give you the examples that I have tonight in it and show you how to do it, but it might just be something you might want us to look a little bit ahead at and look into. And I'm going to start there on, this is Wednesday night, next Monday. I'm going to start there. This is the last piece in the digital book that I'm going to do, but it is something that I think is very important for you to be able to do, because it is one of the few things that really, if you can't think about how to do something and you then identify, oh, that is the negative of something, think, well, what if I took the positive of it and then wrote that down and then did the flip or the De Morgan of it, then put that in, and it works. Now you can say, well, yeah, but I can take that positive logic, take it to a bit. In other words, take that positive logic, the combination of it, take it to a bit, and then take the negative of that bit and use that. And that's true. You can. You can. It takes more time and more energy and more bits of logic to do that, but you can do that, and that works. You follow what I'm saying? You can do it two different ways, but you can use De Morgan as a way of thinking about, oh, I'm trying to think of the negative of something, and I can take the positive of it, and then I've got a really good example of that, which I'm going to hopefully start with on Monday night, and maybe that'll help. Okay, that makes sense. This is not hard stuff, but if you've not gone through this at all, it makes sense to at least touch the base and try to see now. Oh, that's why that's it. Oh, that's why that's it. Oh, yeah, I understand it now. Where I at least have a place that I can go back and look at and at least have some place to reference it to. Because we are going to be using integers, we are going to be using floating point numbers, and we're going to be making judgments based on that type of number. We're going to be writing numbers down and then using them as variables and all kinds of stuff. And then we're going to use bits out of those words, and we're going to take bits out of those words, and we're going to be doing things with them. We're going to be doing all the kind of things that we've just been talking about, and we're going to be doing it a lot in this course. So I want you to understand that a number, a 16-bit number is a number, but it's also 16 bits, 16 control bits, and it can be back and forth, and you can flip it back and forth. And with that, I'm done. Any questions? Any comments? Take care. Have a good day.